Hello, my name is Keshia. Today, I'll compare two networks, highlight their structures, and explain what that means for their cybersecurity risks. Before diving in, here's my method. I marked all nodes with a betweenness of 1.5 or higher since that indicates a moderate influence in the network. Any nodes with zero point 0.2 or above were annotated since those are critical bridges. In short, the bigger and redder the node, the bigger the security concern. Here's network 2. What stands out is that risk is spread across multiple nodes instead of concentrated in one place. Key vulnerable connectors include Stealth, Spectre, Shadow, Ghost, and Viper. If one of them fails, the network might slow down, but communication can still reroute. That makes Network 2 very resilient, even though there are still vulnerabilities. Here's what happens if we use a wildcard filter to isolate Stealth. We can see that it links groups together, but it isn't a complete bottleneck. So if stealth fails, communication can still reroute. That's resilience in action. Now let's take a look at Network 3. This network is highly centralized and is being dominated by Nebula and Starhawk. Their between scores are zero point 0.72 and zero point 0.68, making them critical single points of failure. If either node is taken down, the majority of the network becomes disconnected. That makes this structure very fragile when compared to Network 2. Here's Nebula filtered. We can see how almost every connection routes through this single node. If Nebula is compromised by malware or outages, this could ripple across the entire system. If Nebula fails, the entire network essentially collapses. Both networks have 50 employees, so they're equal in size, but the way they're connected tells a different story. For network 2, notice how almost all the nodes are green? That's because overall, between the scores are generally lower, so no single point can take this system down. My recommendation here is to monitor mid-risk connectors like Stealth and Spectre and add backup so the network keeps running if one node fails. On the right, Network 3 is dominated by Nebula and Starhawk. Their betweenness scores concentrate all risk into two nodes. If either fails, the entire network breaks apart. That's why this client needs redundancy to reduce dependence on these bottlenecks. In short, distributed networks need monitoring, centralized ones need backups. Network 2 is resilient because of its distributed design and it spreads risk. If stealth fails, the system slows down but keeps running. Network 3 is fragile since it leans too heavy on Nebula and Starhawk, and if either fails, the whole network collapses. That's why resilience comes from structure, not size. A strong network isn't about numbers, it's about design. And the takeaway for both the clients are clear: spread out risk, protect key connectors, and act now to reduce dependence on bottlenecks. Thanks for watching. Bye.